to come down with a cold, the watery eyes and stuffy nose and the whole thing. I will try to remember to turn off the microphone before I need to blow my nose, but if I don't, that's what's going on. So this is bound to happen sooner or later. It's the first time it's ever happened before, to me anyway. I'm supposed to try to keep these little strips in here to keep my voice going. Okay, so we left off last time at disorders of differentiation. So we're almost done with reproductive endocrinology. And I think I left off with this diagram here, just to go back over it really quickly. So that in a genotypically normal XY male fetus with a functional SRY gene will express testes determining factor that will cause the indifferent gonads to differentiate into male fetal gonads. Those will eventually become testes. Those gonads secrete testosterone and anti-Mullerian hormone. The anti-Mullerian hormone causes regression of the female Mullerian duct. Testosterone causes development of the Wolffian duct. 5-alpha reductase externally causes synthesis of 5-dihydrotestosterone to give internal and external genitalia. Now, normal female development, get a normal XX genotype. In the absence of SRY, the gonads differentiate female. And if both X chromosomes are active, she'll get a set of functional ovaries. Under these circumstances, the Mullerian duct, in the absence of anti-Mullerian hormone, somebody just ran out. I think thought they were going to take the neuroscience test. Anybody ever done that, sat in the wrong class and realized 5 minutes later? Anyway, so in the absence of anti-Mullerian hormone, the Mullerian duct then develops, and that eventually differentiates into the internal female genitalia. In the absence of the testosterone, the Wolffian duct fails to develop and will atrophy. And the structures on the outside that become the external genitalia in the female differentiate without any intervention. So in the absence of 5-DHT, they'll just go ahead and differentiate female. So there are a lot of disorders of differentiation, and none of them is particularly common. They're kind of tragic because they typically involve a lot of stigma against the kids who are born with them. It's really tough for the families, and treating these disorders has not been the proudest chapter in the history of medicine. So while each individual disorder is fairly rare, collectively they're reasonably common, and there's a lot of different ones. I'm just going to go over a few that I think have some relevance to endocrinology and give some of the simpler examples. So one is Turner syndrome, and this is a disorder that produces sterile females with more or less normal genitalia. So occasionally a fetus will come out with just an X chromosome and either a non-functional X or just the single chromosome. Okay. These gonads will differentiate fetal, although in the absence of two functional X chromosomes, the ovaries don't develop. So these girls will be sterile. Okay. The Wolffian duct atrophies, the Mullerian duct develops normally. So the internal and external genitalia are more or less normal. Okay? Kids with Turner syndrome have other issues. This isn't the only one, but we're just going to focus on early development for the purposes of this course. Down here, another one is testicular feminization syndrome. Okay? Now these are caused by androgen receptor mutations. And there's many, many varieties of this disorder, depending on where the mutations in the androgen receptor are. And in fact, there's over 300 separate mutations that have been characterized to cause some aspect of testicular feminization syndrome. So you have an XY boy, expression of the testes determining factor gives male gonads. Those will go on to develop into testes. He secretes anti-Mullerian hormone, which causes atrophy in the Mullerian duct. It also makes testosterone, okay, which normally would result in development of the Wolffian duct and internal genitalia. However, because of the lack of receptors, the Wolffian duct doesn't develop normally. Okay, and so that you won't get normal internal genitalia. The same androgen receptor is used for 5-DHT. So even though this individual will have 5-alpha reductase, again, in the absence of the receptors, the external genitalia won't develop normally either. And in severe cases, these kids will look much more female than male when they're born. Another fairly common disorder is the 5-alpha reductase deficiency. And these boys fail to make DHT in utero. Okay, so there's an XY phenotype. Okay. In the presence of SRY, the Mullerian duct atrophies, they make normal testes. They have the testosterone, so the Wolffian duct will go ahead and develop into more or less normal internal genitalia. However, with a deficiency in the 5-alpha reductase, the amount of 5-DHT is reduced. And so the external genitalia develop abnormally and are more female. And in fact, 5-DHT ends up being really important in development of secondary sexual characteristics in puberty. And so in a real severe case of 5-alpha reductase deficiency, these children are raised as girls, and nobody knows anything's wrong until they don't go through puberty. Okay, maybe one of the most common ones is an adrenal 21-alpha reductase deficiency. Okay, and this affects both males and females. Okay, but it's more severe, at least for differentiation in females. So what happens, this is the 21-alpha reductase here. So this is an adrenal gland, and this is a zona fasciculata. It is a representation of cortisol synthesis. 21-alpha reductase, oops, I'm sorry, where are we here? The 21-alpha reductase is this reaction right here. Okay. If that enzyme is deficient, then in utero, these individuals fail to complete cortisol synthesis. But more important for understanding this disorder, the precursors to cortisol are made and have nowhere to go. They just back up. Okay. Since the zona fasciculata is upstream in terms of circulation from the zona reticularis, these precursors then go into the zona reticularis and increase the amount of dihydroepiandrosterone made in utero. Okay, so these individuals have a normal XX phenotype. They'll go ahead and develop normal ovaries. The Mullerian ducts will develop, giving them normal internal genitalia. However, the excess DHEA is then converted into testosterone peripherally, which can then be converted to 5-DHT, and so their external genitalia will develop male. And that's all for male reproductive endocrinology. Yeah, before we go to female, let's do a question. If I can get it up here. Yeah, this one. Go ahead and get logged on. People more or less ready? Okay, so this is a pretty hard question, I think. So the question is that, so the males also get 21-alpha reductase deficiency. It's not sex-linked, okay? But because they don't have, it doesn't result in a disorder of differentiation. If it's mild, it won't go diagnosed until adulthood, okay? At which time a lot of these kids end up being sterile. Actually, a lot of times they don't find out until they're trying to have kids. So which hormone is low in this case? Okay, you're awfully quiet today. You're not going to find this in your notes. This one you got to think through. Okay. So I won't bother to ask how many think they got it right. Again, this was a hard one. Okay, so the answer is luteinizing hormone. So there's a couple of ways you can approach that. One is that you know luteinizing hormone is required to make sperm, right? So it would make sense that there'd be a deficiency in luteinizing hormone if sperm production were deficient. But the reason they're deficient in luteinizing hormone production is that they have the same effect as women. They're backing up their adrenal cortisol and to a lesser extent aldosterone synthesis backs up, producing more precursors for adrenal androgens. Now, normally in men this doesn't matter. Adrenal androgens are not a significant source of total androgens. Individuals, men with this syndrome, have more of these adrenal androgens in their system, which don't really affect them very much, except when it comes to feedback inhibition. So these androgens don't really contribute to sperm production because the concentration of the testes is nowhere near high enough to have an impact. But they are high enough to have feedback inhibition to reduce LH and essentially render them sterile. When I used this question on a test, people didn't do very well on it either. Yeah, so this was a hard question. They can't all be easy. Yeah, I think it's right about how many people got it on the test. Okay, with that, let's go to female reproductive endocrinology. Okay, and we'll start this one like we have the others with hypothalamic pituitary control. There are 2 menstrual cycles in women. We'll look at the hormone secretion feedback control during the cycles, which is probably the most complicated thing we'll go over. And then the events right at the onset of pregnancy. So the hormones early on at least should sound familiar to you. Okay? We've got the hormones in the HPA axis, gonadotropin releasing hormone, LH and FSH. Steroids are now from the ovary, they're estrogens, and the precursor hormone progesterone now becomes an important player. And there are 2 new ones we haven't described yet, inhibin and activin. So inhibin and activin activate and inhibit FSH transcription. They're produced in the ovaries and related to anti-Mullerian hormone. Okay? And so that means they bind to a receptor serine threonine kinase. So inhibins are glycoprotein. They have a 20 kilodalton alpha subunit that's glycosylated and a 12 kilodalton beta subunit, so they're glycoproteins. Activins are also, I'm going to call it a glycoprotein just for simplicity's sake, although it's not actually glycosylated. Instead, it has the two 12 kilodalton beta subunits. So the way they work is that activin will bind to the type 1 receptor, and that causes the type 2 receptor to bind. The type 2 receptor is phosphorylated. It turns around and phosphorylates the SMAD transcription factor, and that activates transcription of follicle-stimulating hormone in the pituitary. Now, inhibin works by competing for the type 2 subunit. So what happens is there is this inactive subunit. It's got the receptor portion, but notice it doesn't have a kinase on it. That's the one that binds the alpha subunit, the inhibin alpha subunit. That causes this type 2 subunit to bind. But without anything to autophosphorylate, it just remains inactive, taking away the activity from the activin. So we lose this transcriptional program that stimulates FSH transcription. So that's downregulated. So I won't mention activin again because it's sort of passive in this. It's the real action is occurring through inhibin. Okay. And it's worth pointing out both these hormones are present in men and do about the same thing, but they're not. I didn't bring them up because it's not that interesting in men. It doesn't really tell you much about how anything works. Okay, so there are some differences between men and women in how the HPA axis works. As in men, in women, the expression of gonadotropin-releasing hormone is sort of the first sign that she's about to go through puberty. Okay? And this is a transition to a more or less lifelong reproductive state. Okay? So in childhood, her gonadotropin-releasing hormone levels will be very low. Okay? This is during the day and at night. And right at the onset of puberty, she'll start to secrete gonadotropin-releasing hormone in whatever her characteristic pulse frequency will be, somewhere between 30 minutes and an hour and a half. One pulse every 30 minutes to an hour and a half. But it'll only occur at night. During her reproductive years, the pulses even out. They're the same during the day and during the night. And again, they establish this very regular pattern. Okay. Now, in puberty, aside from the gonadotropin-releasing hormone, also ovarian estrogens are synthesized as well as peripheral androgens. And these are responsible for development of secondary sexual characteristics, things like breast development. Now, menopause is the end of the reproductive years in women. Okay? And gonadotropins tend to go up after that period. So, again, menopause is the end of the reproductive years. Usually occurs somewhere around 50 years of age. And it's not a discrete event. It comes on slowly. Usually takes anywhere from 1 to 5 years to really complete. Okay, so here is, this is going to be estrogens and gonadotropins throughout the life. Here's birth. Menopause out here at about age 50. These will represent monthly menstrual cycles. Okay. And at menopause, the ovaries stop responding to LH and FSH. So estrogens decrease. So if we plot estrogens, again, there's this little rise in pregnancy and right after birth, and then at puberty, and then these represent the monthly cycles. There are 2 peaks of estrogen. And then at menopause, they go down, and the ovaries stop responding, and so estrogen is no longer produced. However, luteinizing hormone and follicle-stimulating hormone, while they follow the same pattern as estrogen throughout the lifetime, they actually go up during menopause. Okay? As does gonadotropin-releasing hormone. So it goes from this characteristic adult level to a much higher level after menopause. And that's due to lack of feedback inhibition. Okay. The other important effect of menopause is that the individual loses the proliferative activity of estrogen. Estrogen is a growth factor. And as levels go down, a lot of essentially aging occurs. Okay, so gonadotropins control the menstrual cycles. Now, there's actually 2 separate menstrual cycles in women that overlay on top of one another. The first is the ovarian cycle. This is the one that occurs in the ovaries and involves development of an oocyte in preparation for fertilization. And it's this cycle that drives steroidogenesis. There's also the endometrial cycle, which targets the endometrium of the uterus. And this prepares the uterus to accept a fertilized embryo for implantation and pregnancy. Okay, so here is the endometrial layer of the uterus, and here is the ovary, and this is a developing follicle here. Okay. So the ovarian cycle, we'll go over that first since that's where the hormones come from. Okay. It lasts 28 days. There are two phases. The first phase is the follicular phase. The second phase is the luteal phase. The follicular phase starts with the recruitment of a cohort of follicles. So this is a group of follicles within the ovary that they come in as a group. Each has an immature oocyte in it. Okay? One of these will become dominant, and it will be the one that develops an oocyte. Finally, the rest of these will die off, and the oocyte will be developed. And right in the middle, at around day 14, 15, is ovulation. That's the release of the developed oocyte that can now be fertilized. Okay. At ovulation, the luteal phase starts. Okay. The follicle now differentiates into a structure called the corpus luteum. And this corpus will grow, it's highly vascularized, and it will produce steroids, a very large amount of steroids. Eventually, feedback inhibition reduces the amount of steroids the corpus can produce. It differentiates into a corpus albicans and is expelled. And now the endometrial cycle parallels the ovarian cycle. Okay? So down here we have our 7 steps. All right, and the purpose of the endometrial cycle is to prepare the endometrium for pregnancy. Okay. So we'll start it just so it parallels the ovarian cycle. We'll start it during menses, which is the breakdown of the uterine wall, breakdown and narrowing of the uterine wall. There's then a proliferative phase, and this is under the influence of follicular steroids, the buildup of the uterine wall layer, thickening. And then after ovulation, it differentiates into a secretory phase, endothelium. So it stops growing, and it forms structures that allow it to accept a fertilized embryo. Okay. And this prepares the endometrium for fertilization. Okay. So I'm going to put this up, and I don't want you to panic when you see it, because it's complicated. And actually, if you take the ones out of the textbooks, they're the medical textbooks, they're actually even a lot more complicated than this one. We'll go through it step by step. It won't be so bad. Right, so here is the ovarian cycle, follicular and luteal phase, ovulation right here in the middle, endometrial cycle's up here. This is luteinizing hormone. Okay, you can see a peak right here before ovulation, which is the key feature. This is follicle-stimulating hormone. It's also got a peak, nowhere near as prominent. This is because of inhibin. And there's also a peak out here right at day 28, which is critical. This is inhibin, and it goes roughly opposite of FSH. So as FSH starts to go down here, you can see inhibin peaking. And this peak of FSH here corresponds with this dip in inhibin synthesis. They're the estrogens, which have 2 peaks, one here before ovulation, and before we have the LH and the FSH peak, and then one here during the luteal phase. And finally, progesterone, which occurs here for the first time as a hormone. It's low during most of the follicular phase and really reaches its peak in the middle of the luteal phase. And it's really progesterone as a steroid that dominates the luteal phase. So the maturation of an oocyte occurs in a follicle. Okay, this is a secondary follicle at about day 10 of the ovarian cycle, roughly 4 days prior to ovulation. Okay, in the center here is the oocyte. Okay, it's undergoing maturation, and eventually will be expelled during ovulation. There's also extensive steroid synthesis in this follicle. cell layer on the outside is called the theca, and that's where androgens are synthesized. And on the inside, these cells here are granulosa cells, and they synthesize estrogens and progesterone. Now, the organization here is similar to what we saw in males with the testes, so that the theca roughly correspond to the Leydig cells, and the granulosa roughly correspond to the Sertoli cells. But there's only one germ cell, whereas there's almost unlimited germ cells in males. And there's a 28-day cycle, of course, and there's nothing like that in males. Okay? And that 28-day cycle dictates extensive development of this follicle, which is then expelled, whereas in males that doesn't occur. So the start of the ovarian cycle is driven by the decrease in inhibin causing an increase in FSH. So this is right here at day 28. That results in a process that's not well understood in the recruitment of a cohort of follicles. So a group of follicles comes forth, and they're going to be the ones to develop. The theca and granulosa cooperate in estrogen biosynthesis. Estrogens cause cell proliferation, and the dominant estrogen is estradiol, E2. And under this influence, one follicle will become dominant. So let's go over the steroid synthesis. So this is a thecal cell. This is a granulosa cell. This is pretty similar to the diagram I showed last week in male steroidogenesis. Okay, so luteinizing hormone then binds to a G protein coupled receptor coupled to alpha, G-alpha S, activating protein kinase A. Protein kinase A activates a transcriptional program that results in increased synthesis of steroid acute regulatory protein and cytochrome P450 side chain cleavage. That increases androgen synthesis. Androstenediol here then is secreted and accumulates in the granulosa where there's 17 beta hydroxylates that will convert into testosterone. Okay? So thecal androstenedione and testosterone don't circulate. This is not a significant source of circulating androgens in females. In the follicular phase, the granulosa makes the estrogens. Okay, so here's an FSH receptor. It's also G-alpha S coupled. Okay, so protein kinase A activates, leading to a transcriptional program that causes synthesis of aromatase. Right? And this is the enzyme that converts androgens into estrogens. Right? That's one of those enzymes I'd like you to have memorized. These estrogens, E2 and E1, circulate in females. Okay? They also combine with the estrogen receptor to induce a transcriptional program that leads to synthesis of inhibin and more FSH receptors. That's important. Okay? So what you end up getting then is the inhibin is secreted and the FSH receptors start to accumulate on the surface of the follicles. Estrogen also causes granulosa cell proliferation and oocyte maturation. Okay? So now in the next slide, we're going to look at feedback in the middle of the follicular phase. So we're right around in here before these big increases in LH, estrogen, and FSH. So the follicular phase feedback selects the dominant follicle and leads to an estrogen surge. Okay, so here we have inhibin and estrogen being synthesized. This is the follicle that's going to become dominant. Okay, but they're all synthesizing inhibin and estrogen at this point. Estrogen and inhibit FSH and GnRH, as well as the inhibin coming from the other follicles is an inhibitory factor on the FSH. Estrogen is feeding back and causing more FSH receptors to be synthesized and more inhibin to be synthesized. Why one of these becomes dominant is not clear. It may just be stochastic. It's just one of them has to be a little better than the others, and that one becomes the dominant follicle. Where are we here? There's 3. Okay. So estrogen causes proliferation and synthesis of more receptors. It also sensitizes So again, this is a poorly understood process, but it makes the secretion of FS, it sensitizes the GnRH receptors so that whatever signal you do get, even though you've got feedback inhibition here, you do get secretion of what FSH is there. Okay? So there's low-level FSH secretion. Okay? Now this is not enough to allow estrogen synthesis in these follicles that haven't done such a good job of synthesizing FSH receptors. Okay? But it is sufficient to keep the dominant follicle going. Okay? That allows more synthesis of protein of aromatase, which keeps estrogen increasing, and so estrogen starts to surge. Okay, and that gives you what amounts to a positive feedback in allowing this dominant follicle then to take over. Okay, now we're moving over into here, and we're going to go over the events right at ovulation, just before and right at ovulation, around day 14 or 15. So this estrogen surge ends up leading to ovulation. So here we've got the surging estrogen with the feedback inhibition, the inhibin with the feedback inhibition on FSH. Now something, if you're trying to learn this stuff, really annoying, but in a way almost magical happens, is that estrogen, which was involved in negative feedback, is now involved in positive feedback. It just changes roles. Again, the molecular basis of this change is not understood. Okay, but estrogen now stimulates synthesis of LH and FSH. FSH is still lower than LH because of the effect of inhibin. It also stimulates the production of gonadotropin-releasing hormone. That leads to a surge of LH and then a surge of FSH. So that what it amounts to is there are three surges. Okay? The first is estrogen as a result of the proliferation of the dominant follicle. The second is LH, and the third is FSH. And that order is absolutely critical. Okay? And that ends up leading to ovulation. Okay, so ovulation is the release of the mature oocyte. And that heralds the beginning of the luteal phase. The dominant follicle differentiates into a corpus lutein. It's highly vascularized. It's rich in LDL receptors. And it increases steroidogenesis almost 20-fold. The key changes are that the granulosa lutein starts to express LH receptors. And that leads to the synthesis of progesterone. So here's a luteal phase theca lutein, which increases its androgen synthesis. It's still got LH receptors. Now PKA's transcriptional program leads to stimulation of LDL receptors, additional LDL receptors, which increases the precursors for steroidogenesis. It also stimulates synthesis of steroid acute regulatory protein and the side chain cleavage enzyme to boost androstenedione synthesis, which then diffuses into the granulosa lutein. The granulosa lutein, which is in the luteal phase, produces progesterone. Okay, so here's the FSH receptors. FSH then activates protein kinase A. Leading to synthesis of aromatase and estrogens. So there is that second estrogen surge. It also develops luteinizing hormone receptors. Okay, now the luteinizing hormone does the same thing in the granulosa lutein as it does in the theca lutein. It leads to synthesis of LDL receptors, steroid acute regulatory protein, and cytochrome P450 side chain cleavage, which ends up becoming, with the 3-beta hydroxylase, progesterone. Okay. However, the granulosa lutein does not have the 17-alpha hydroxylase, so it can't continue the synthesis pathway on its own. Okay. Therefore, what happens is this progesterone becomes the source of the circulating progesterone during the luteal phase, as well as some of it leaks back over into the thecal lutein, increasing androgen synthesis all the more, which causes an increase in estrogen synthesis. Okay. Now, don't let the fact that these signaling systems are the same bother you. There has to be some sort of localization or something that directs the two separate PKA-based programs. There are multiple isoforms of PKA, but again, the basis of this is not well understood. Okay, so luteal phase feedback. Progesterone is an anti-estrogen. Okay, so this is the way I want you to think of progesterone. When you see estrogen, estrogen's a growth factor. Every place you see estrogen, something's proliferating, something's growing. Okay. Progesterone inhibits that, so it's kind of an anti-estrogen. Okay, so we're here in the luteal phase. Okay. We're secreting estrogen, progesterone, and inhibin. Progesterone and inhibin, there's no confusion, there's no positive feedback. These are all involved in negative feedback. So LH and FSH decrease from their surge levels. That reduces their ability to promote estrogen synthesis. So the amount of estrogen, progesterone, and inhibin decreases. That reduces the positive feedback effect. And importantly, the proliferative effect of estrogens. That causes the corpus lutein to atrophy and eventually to stop producing progesterone and dramatically reduce inhibin synthesis. Corpus lutein differentiates into a corpus albicans and is expelled. Here we're right at the end. With very low inhibin concentrations and reducing, that releases this brake on FSH synthesis. That increases and causes selection of another cohort of follicles. Okay, so the follicular phase steroids now drive the uterine development during the endometrial cycle. So we started this overlaying it over the follicular and luteal phase, starting with menses. And there's no steroid influence during menses. During the proliferative phase, estrogen dominates. Remember, estrogen is a growth factor. So this proliferation of cells in the endometrial cell wall occurs under the influence of estrogen. Progesterone stops this proliferation under the influence of estrogen and causes a differentiation into secretory phase endothelium. So we're here in the proliferative phase. Okay, estrogen is involved in negative feedback here. Proliferation of the dominant follicle, FSH synthesis is low. This estrogen then binds with the estrogen receptor, and that's what leads to the program that gives more estrogen receptors and further proliferation of the endometrial cell wall. Okay. This increase in estrogen receptors, again, is kind of a positive feedback loop. Okay. So this positive feedback means the increase in estrogen leads to more estrogen receptors and an increase in epithelial cell layer thickness. So secretory phase uterine endothelium occurs after ovulation. Okay. So now we've got progesterone, and it has a receptor similar to the estrogen receptor. Its transcriptional program leads to an increase in the synthesis of the 17-beta hydroxylase that converts E2 to E1. This is a reversible reaction. E2 is a more potent steroid. It also leads to synthesis of E1 sulfatase, or estriol sulfatase. Okay? And if you remember way back from, I think, the first or second topic, sulfating a steroid is a way to inactivate it. Okay? So we start with estradiol, which is more abundant and more potent. Synthesize excess 17-beta hydroxysteroid dehydrogenase, leading to more estrone, which is less abundant, less potent, but importantly is converted by estrone sulfase to estrone sulfate, which is inactive, and this is an irreversible reaction. Excuse me. Okay, so this accumulation of inactive estrone sulfate means that E1 and E2 have to be reduced. Okay? That leads to the loss of the synthesis of the estrogen receptors and estrogen's transcriptional program, and that was what leads to the differentiation of the endometrial cell wall. So the secretory epithelium is optimal for implantation for only about 4 days. Okay, and that gives you about a 24-hour window for fertilization, where fertilization is the most likely. Okay. Once you get past that window, when menses starts, then implantation can't occur. It doesn't matter if the oocyte is fertilized after that. There's just no place for it to be implanted. Okay. And this occurs unless that one is fertilized, and then the blastocyst or embryo starts to secrete placental hormone variants. Okay? So these are all releasing hormones and many anterior pituitary hormones. And they're not subject to feedback inhibition because they're not coming from the anterior pituitary. Okay? Those stimulate steroidogenesis from the placenta and the fetus. And what allows this is the synthesis of this one key early hormone, chorionic gonadotropin. And that hormone allows the entire fertilization and implantation to continue without being interrupted by a menstrual cycle. Excuse me. So chorionic gonadotropin is in the same family as LH, FSH, and TSH. Okay? So they have identical alpha subunits and different beta subunits. It's very similar to LH. And what it does is it binds the LH receptors with equal affinity. Okay? And this stops the mother's cycle to preserve that secretory phase endothelium so that the embryo can develop and menses doesn't commence. It does this by keeping steroid synthesis high, excuse me, steroid synthesis high, and is not subject to feedback inhibition. It's expressed throughout pregnancy, but is really at its highest in the first 6 weeks. So chorionic gonadotropin extends the secretory phase of the menstrual cycle. So we have chorionic gonadotropin here, leading to synthesis of progesterone. Okay. That progesterone decreases, the feedback inhibits the luteinizing hormone release, but of course we're not worried about that synthesis. We're not worried about that, so we have the chorionic gonadotropin. Okay, that keeps this transcriptional program going and keeps this secretory phase endothelium preserved so that progesterone synthesis stays high. And I should say the chorionic gonadotropin is commonly abbreviated HCG, or human chorionic gonadotropin. That notation drives me crazy because we don't call anything else human, but that's what everybody calls it. Sounds easy, so I'll stick with the HCG. I'm sorry. Okay. So again, the progesterone maintains the secretory phase endometrium and it can now accept and support the development of the blastocyst. Now, very high steroid levels are required to maintain pregnancy. Okay. So early, human chorionic gonadotropin stimulates estradiol and progesterone from the corpus luteum. But after 8 weeks, the placenta takes over this function. Okay. And the levels of steroids are very high. So if this is prior to pregnancy, this is the beginning of pregnancy right here. This is the gestational. Yeah, excuse me. This is the gestation. Does anybody want to take over? This is the gestational age in weeks. It's progesterone. And you see this is a log scale. So up at its highest, the progesterone here, normally its top is about 8 nanograms per mil. At its highest, it's nearly 100 nanograms per mil. E2 is 20 nanograms per mil. whereas usually it's less than 1 nanograms per mil, even at the peak of the menstrual cycles. So there's a new estrogen involved here. It's estriol, or E3. It's distinguished because by the 16 alpha hydroxyl group here. It's not clear exactly what E3 is doing, but it's known it's required. And its synthesis requires fetal enzymes. Okay? And this is the key to what's going to be called the placental fetal maternal unit. So the mother placental fetal unit, the mother requires very high levels of steroids to maintain the pregnancy. And she also requires E3 amongst those steroids. The fetus requires a mother and a placenta. But also, as we saw during the disorders of differentiation, it's important to limit the fetus's exposure to androgen and estrogens, even though the mother has very high levels of estrogens. What the mother supplies then is LDL for cholesterol. She lacks the steroid biosynthetic capacity, though, to convert it to steroids. The placenta has high levels of a lot of the enzymes that are required for steroidogenesis, but lacks the ability to make its own cholesterol and some of the other key enzymes. The fetus, in its developing adrenal gland and liver, have the enzymes that the placenta lacks. Importantly, this unique 16-alpha hydroxylase and a sulfosyltransferase, but lacks the ability to absorb cholesterol and doesn't have aromatase and the 3-beta hydroxysteroid dehydrogenase. Okay, so this is the mother, this is the placenta, this is the fetal adrenal and liver. So LDL from the mother is transported into the placenta, where it becomes pregnenolone. The pregnenolone then passes to the fetal adrenal gland, where the sulfosyltransferase makes it pregnenolone sulfate. It's then converted into DHEA sulfate. The placenta will also make progesterone, which is the source of the high levels of progesterone in the mother. Now, this DHEA sulfate passes to the fetal liver, where the 16-alpha hydroxylase resides. And that makes DHEA sulfate hydroxyl, hydroxyl 16, anyway. These pass back into the placenta, where there are special enzymes that reverse this reaction. Normally, these reactions aren't reversed. This DHEA hydroxate then becomes estriol, E3. Could also make from DHEA E1 and E2, and those pass back into the mother. And so unless each of these parts is functioning correctly, the pregnancy won't be maintained. Okay, and that sets up a dependency to cause the fetus to go through development. So I told you that was complicated. Aren't you glad it's not on this test? Now, it's at this point, usually people are pretty wrapped up with the first test, and so at some point people will start to panic about all this stuff. On the final, I'm going to give you the questions. Okay, so a few weeks before the final, a couple weeks before the final, I'll put out another little study guide. And on that study guide will be the 15 finals questions I'm going to ask. Not the answers, but the questions. And some of the questions will be pretty general, but it will tell you what you need to study, all right? Incidentally, that hasn't changed the class average over the years, just, but it seems like the decent thing to do. Okay, so let's do another question. Let's do an easier one. Since I feel bad about the class performance on the previous one. Okay. That wasn't too bad, was it? Yeah. All right. Who's hissing up there? Okay, so all right. So if you said it was a positive feedback loop, first thing to remember is, especially for exam 1, almost everything's going to be negative. Okay. Second thing to remember is that, so even if you don't remember what CRH and ACTH did, right, they're in the, you know that at least they're in the same loop. Okay. RH means it's a releasing hormone. Okay, so the other one has to be is probably it's TH, adrenocorticotropic hormone, okay, which means it's a pituitary hormone, anterior pituitary hormone. Okay. When we talk about a loop, we're referring to the part that goes back. Right? So corticotropin releasing hormone, CRH, causes release of ACTH. But when the loop part is the feedback inhibition, so it's a negative loop. And if you thought it was a long negative feedback loop, again, the way to avoid that mistake is you know there's other hormones involved. So you start with CRH, ACTH, and then the third one would be cortisol. That's the one secreted from the adrenal gland. That would be where the long negative feedback loop would occur. Okay, so if it's the pituitary and the hypothalamus, it should be the short loop. Okay, let's do, what time is it? Yeah, we got time here. Let's do one more, let's do another one here. I'll leave one for the end. All right, so what property is shared by thyroid hormone and testosterone? Right, we just heard about testosterone. So even if you haven't studied or remember much about it, you should know a little bit about it. We went over thyroid hormone. If you haven't gone over that yet, then you need to get rolling because the exam's coming up pretty soon. Does that 100% means, does that mean everybody's answered? I don't know what all these bars mean. No? More people are still answering. All right. All right, 5 more seconds here. Okay. So clearly the idea here is that in a lot of ways thyroid hormone is like a steroid and testosterone is a steroid. So you just need to find kind of the steroid property they have in common. Okay? So the half-lives, this is a really short half-life. Thyroid hormone's a lot like, well, let's go to the reports. Thyroid, let's see if anybody actually answered that one. All right. So we know testosterone doesn't signal through G-alpha S receptors. It's a steroid. Only the protein signal through that kind of receptor. Okay? You really need to have that down. Progesterone can't be a biosynthetic precursor of thyroid hormone. Thyroid hormone has a unique biosynthetic pathway. Okay, so, all right, that'll be it for those then. And with that, we'll go on to our last topic and our shortest topic. This is lactation. Lactation is actually about 3 hormones, but 2 main ones, oxytocin and prolactin. And this is the classic positive feedback mechanism. Okay, so lactation. During pregnancy, there's extensive breast development under the influence of mostly placental hormones. If we do a cutaway of a lactating breast, we see these purple structures are secretory lobules. Inside the lobule, we have these little sacs called alveoli. Inside, if we do a cutaway of the alveoli, in the middle is the milk. It's secreted from these epithelial cells here that are called alveolar cells. They actually produce the milk. And they're surrounded by a layer of smooth muscle, which are actually the cells that are involved in contracting and ejecting the milk out of the alveoli. So oxytocin is a posterior pituitary hormone. Right? It's one of 2. It's a small peptide, it's only 9 amino acids, and it's related to antidiuretic hormone. I think there's a 1 amino acid difference. Okay. Hormones are made in large neurons in the hypothalamus. They travel down the axons and are released into the bloodstream here at the posterior pituitary. Therefore, regulation requires neural inputs. Now, oxytocin targets smooth muscle and causes contraction. Okay. This is true in the secretory lobule, where it causes milk ejection. The other big function we won't talk about, but I want to mention, is it's very important in contraction of the uterus at birth. And it also acts as a neurotransmitter. It's been co-opted by evolution as a neurotransmitter, and it's essential for forming normal relationships with other people. It's almost Valentine's Day, so why not? Okay. It works through a G-alpha Q, like you'd expect a hormone, having to do with attachment and affection. It works through a G-alpha Q coupled protein. Okay. Actually, you wouldn't expect that. Anyway, so it works through a G protein coupled receptor coupled to G-alpha Q. Okay. That activates phospholipase C beta, causes release of intercellular calcium stores. And those of you who know much about muscle will know that causes contraction of muscles. Calcium leads to contraction of muscles, which is somebody else's unit. So the last one is in the anterior pituitary. It's actually second to last. That's prolactin. Prolactin is a large peptide with a structure similar to growth hormone. Therefore, the receptor is similar. It's a tyrosine kinase coupled receptor. Okay. And it modifies through the JAK-STAT kinase transcription factor complex. It modifies gene expression to produce the many proteins required for milk production. It also inhibits gonadotropin releasing hormone release, which leads to a decrease in LH and FSH. And therefore, high levels of prolactin will result in stopping menstrual cycles, so that a woman's either lactating and devoting her energy stores to that, or she's pregnant and devoting her energy stores to that. Okay, and this is called lactational amenorrhea. Okay. So prolactin secretion is also dominated by neural inputs. Okay. And the dominant hormone is prolactin inhibiting hormone. Okay. Now, thyrotropin-releasing hormone is also involved. Oh, here's prolactin-inhibiting hormone is the neurotransmitter dopamine. Okay. It's related to epinephrine, so it's an amide hormone. Thyrotropin-releasing hormone is involved, and it activates protein kinase C, and that results in a transcriptional program that, along with estrogen, causes transcription of the prolactin gene. Now, as long as prolactin-inhibiting hormone is bound to its G-alpha-I coupled receptor, prolactin's not released. When that's reduced, a constitutive adenylate cyclase is activated. Protein kinase A, active protein kinase A then results in the secretion of prolactin. Okay. So the regulation here is driven by positive feedback. Now, initially, this pathway started by crying of the baby. And crying of any baby won't do. It has to be your baby. Some women are more sensitive. But you're very attuned to the crying of your own baby, at least if you're a woman. and that will cause the release of the prolactin-inhibiting hormone and oxytocin. Okay? But once the suckling starts at the nipple, okay, there are mechanosensitive receptors in the nipple that are attached to the nerves that signal to the spinal cord. And in the spinal cord, up through the central nervous system, a signal is sent to release oxytocin through the posterior pituitary to cause contraction and eject the milk. Okay? And this is the same response that caused the maternal emotional response. And thyrotropin-releasing hormone and estrogen, which have been promoting synthesis of prolactin, now prolactin-inhibiting hormone is reduced by the same neural input, allowing prolactin to be released, increasing milk synthesis. And so as long as this suckling behavior continues a couple times a day, the woman will continue to produce milk through this positive feedback mechanism. Okay? Anybody here grow up on a farm? Nobody grew up on a farm. This is how it works in dairy cows as well. As long as you keep milking a dairy cow, she'll keep producing milk for you. And it's because of this activation of the nipple. Okay. Now we also have GnRH here, stimulating LH and FSH release. But prolactin inhibits GnRH release. Okay. And that keeps the menstrual cycles from commencing. And so as long as a woman's actively lactating, she doesn't go through menstrual cycles, and she can't have another pregnancy. So this really means that she has to feel like the baby's well enough to be on its own and release it from breastfeeding before she can get pregnant again. Okay, and that is lactation. Let's do one more question. So this one's going to have an introduction to it. All right? And I bring this up not because I really expect you to get this one right. This is another really hard question. But because I want you to know how much you know. Okay, you should be able to follow this story. So the first part of it is, does anybody know who these guys are? Yeah, so actually you know, so you guys actually, the last class had no idea who they were, but they got really good results on the test, so we'll see if there's a correlation. So these guys got in trouble for performing enhancing drugs. And I remember reading about it a couple years ago. And the drug they found in their system was chorionic gonadotropin, which is on the list of banned substances. Okay? Because it was considered evidence of having used what they call anabolic steroids, or what we would call androgens, or androreceptor agonists. And I thought, well, why? And it turns out that, you know, where does HCG come from? Well, it comes from a developing blastocyst. You know, what reason would a male have to have that? Okay? And actually, they originally argued that it was natural, that they had, and they've got to be incredibly rare, but there are these amazingly rare tumors that might cause some HCG in a man, but that's not what happened in this case. Okay? So there's no real reason for these things to occur naturally in males. Okay? It has been tried as a fertility treatment, but it's not really a very good fertility treatment either. Okay? So the key to sort of understanding this is people abuse anabolic steroids for the purpose of, you know, developing those phenomenal cosmic biceps. Okay? But there are other physiological consequences to androgen abuse. And so you want to think feedback. And before I give you the question, here's a hint. Think about it. I can usually, as people figure out what the hint means, it sort of rolls around the room. It's like, oh, all right. Okay, so why do androgen abusers often undergo a course of therapy with HCG after they are off the androgens? Yes, that's what they refer to it, I think. At least that's what they used to refer to it, as the juice. This is something else we're not finding in the notes, those of you who are looking. Okay. That's what the raisins are supposed to mean, right? Ah. All right. This has to do with feedback inhibition, all right? So so first of all, anatomy. The androgens, the testosterones that support spermatogenesis are at very high concentrations and are made right next to the Sertoli cells. Now, you can inject androgens into your arm all you want, but that's not anywhere, and it will support muscle development. It's very good at that, but that's nowhere near a high enough concentration to support spermatogenesis. What it is a high enough concentration to do is to cause very powerful feedback inhibition to the pituitary hormones. Okay? So not only aren't you taking enough of the testosterone to support spermatogenesis, but you're not making enough LH and FSH to keep them from atrophying. And that's one of the nasty little side effects of androgen abuse. Okay. The HCG then is taken in an attempt, it's outside the feedback loop. And so it's taken in an attempt to jumpstart testicular development and resume normal reproductive activities. So you can think about that next time. And it really generated a lot of Lance Armstrong jokes, not one of which could I come up with that was fit for this audience. So, so with that, that's all I have. I want to say a couple things about the test. The first thing is that the neurobiology on this issue is very, very clear. All-nighters don't work. You have to get some sleep to encode memories. Okay, memory encoding happens while you're asleep. I mean, you can, if it's okay to stay up and like write a paper or something all night. It may not be optimal, but it's all right. But all-nighters for tests don't work. Second thing is, when people come to me and they say, oh, Dr. Brownhouse, I studied so hard, I really knew the material, why didn't I do better? Most of the time it comes down to test-taking skills. There are going to be some questions that are hard. Okay, they just are. There are going to be some questions that are easy. Do not psych yourself into thinking that the easy questions are hard. Right? I used to tell people that, look, I'm not a diabolical genius. I'm not trying to fool you. After a few years of this, I've come to the somewhat troubling conclusion that maybe I am too a diabolical genius. There are some questions that are easy. If you look at the question and it's an easy question and you know the answer, don't psych yourself out by thinking, oh my God, it can't be this easy. It might be this easy and you might just know it. So answer it. Okay? And I'll see everybody Thursday morning, and good luck.